thanks the organizers to give me this great opportunity to be here and also to take care of everything and also the support, financial support. Otherwise, I'll not be here. So today I'll talk about this quantum algorithm for simulated wave equation. It is a joint work with Stephen Jordan, where he's currently working at Microsoft at the quantum architectures at Redmond, Washington. I had a great opportunity to work with him this year at Microsoft as a researcher, visitor researcher during 1 week. And Errol Strander, that works in QUICS, the Joint Center of Quantum Information and Computer Science. I started this work during the time that I went there 2 years ago at the University of Maryland, and Stephen Jordan was a researcher there in the age. We can find the results in the archive page here, but you have now a better, update version that hopefully will appear until the end of, until in the beginning of the next year, and hopefully you can see it soon. So here's the outline of the presentation. I will quickly talk about some techniques to solve a partial differential equation, the ordinary ones. Then I will talk how we can deal with the same kind of problem using the quantum algorithms. And then finally, I will talk about our result and the final considerations. So there are two main techniques to deal with the differential equation numerically. They are the difference and the finite element methods. And so they are largely employed to solve partial differential equations when you have to deal with different complicated geometries, boundary conditions, so you don't have an analytical solution. So for instance, in finite difference methods, I just showing the one-dimensional case. You have to back to the basic definitions of derivatives, okay? So here we can see how we can approximate for the first derivative. There are two different approaches, the forward and backward. And here, how we can approximate the second derivative. They are just approximations, okay? You can check the order of approximation if you want. There are standard techniques to check that, using, for instance, Taylor expansion. The point here that I want that you take a look is about the second order here, the second derivative, the approximate for the second derivative here. When I write here in terms after the discretize some function that I want to solve, it's just we just have this operator applying some vector. So after you discretize your function, okay. So here, look that this matrix is quite sparse, okay. And now, and also that this matrix depends of the h, where h is the displacement of each point of the LEDs that were describing your problem. So in practice, there are a lot of softwares available if you want to work numerically. Here, I'm focused more on this kind of method. This is a finite element method. I would say this more sophisticated one, because the discretization is in the domain of your function. So you take pieces of subdomain, then you have to link them together with different shapes that we want, triangles, squares, and then we have to check the continuity of your function in this subdomain, and then after the domain, the entire domain, and so on. I talk quickly and superficially about these methods, but if you have some problem to solve, there are three things that you should certify about after the discretization, which are the consistency of your method, the stability of your method, and the convergence, consistency, and stability. These three things that you should certify to see how good you are in your numerical. Okay. So these ordinary methods, in the end, will be clear, but they scored bad. They had bad scales with h, where h, remember that h is the displacement between the points in the lattice. So the question is here, is this promising application for quantum computers? Yeah, so I can say that this paper gave the direction to answer this question. That the quantum, this quantum algorithm to solve linear system given by Arrow has seen Lloyd. Today no one has HHP algorithm, quite known. And the basic idea is that we have an algorithm that we have our oracle that can assess the non-zero elements of sparse matrix, and you have the ability to make prepare a quantum state proportional to B, and then it produce in the end a solution of your linear system with epsilon order closer to real solution. So if you look at the complexity of this problem, you see that the number of qubits as you're dealing with Hilbert space is log n qubits, and then here the time complexity that depends of the sparsity of the matrix. Kappa is the condition number of a matrix squared of the condition number, and epsilon. So it should take attention that this algorithm only gives the great speedups when you are dealing with a matrix sparse and the condition number scales L, and so it's really restrictive in that class of problems. So here you have the Barry result. Here I imagine that Barry knew it about the differential equations, the standard techniques to differential equations, and he knew it that this matrix. So in the end, after you have a problem, after you discretize your problem, you are dealing with a linear system to solve. So I imagine that he knew it that these matrices in general are quite sparse. The condition number depends a little bit of the precision that you want. But also that here I'm dealing with the first order differential equation, but there are different standard techniques that you can convert second and third order differential equations to the first one. And so basically this idea, so then you can see it has a linear system to solve. So at the first moment, Barry applied directly the Arrow HHL algorithm, but he didn't get so good results. Then he did a clever thing afterwards, and he got this complexity of solve these algorithms. So here, I'd like that you take attention of this dependence of the time here, and also the norm of the matrix A. So if you remember after I discretized the second order derivative, you see that the matrix depends of the 1 over h, square h, because the second order derivative, second derivative, sorry. And then the idea is how you take these points and bring it together to check the convergence of your method. More complicated, the complexity increase, okay, in this order here. So, but here, in our case, we are only focusing the wave equation, okay? So we take it another approach. So rather than use an HHL algorithm, we request directly to Hamiltonian simulation. So our algorithm is extremely specialized to wave equation, okay? So doing that, we get a quadratic better performance with the lattice spacing, as I said, that dependence of the lattice spacing in the Barry algorithm, compared with the quantum algorithm proposed by Barry, okay? So let's see the core idea of this algorithm. So here's in the one-dimensional case, the wave equation. So then we can work with this Hamiltonian and the Schrödinger equation. It's a non-diagonal Hamiltonian, and we split your Hilbert space in two subspace. So it's quite simple, this method. So then we have to check here, we have to apply this again, the first derivative in both sides, okay? Doing that, in the end, you have a multiplication of this matrix, and then you see that in this specific case, each subspace is evolving like a wave equation, but it's particular to one-dimensional case. But okay, I just talk about one-dimensional cases. They are not so good problems to solve. I mean, it's pretty simple. I didn't talk about boundary conditions and so on. So then we took advantage from some properties, some knowledge about the spectrograph theory. So for instance, we know that Laplacian can be approximated by this graph Laplacian that I calibrate here by L, sorry. And what's the idea what is the definition of this graph Laplacian? the definition is that we have this matrix big delta here, and this matrix here is just a diagonal matrix that depends of the graph we're working, and this diagonal matrix gives which is a square matrix, sorry, a vertex by vertex. You have to index your matrix, and each vertex in this matrix you put the degree of the graph, okay, each vertex, the degree of each vertex. In this case, in this path graph, for instance, the degree is 2. So that's the reason I have 2 here. And then you have an adjacent matrix of some graph. In this path graph, is just 1 if you have the vertex connected, and 0 if you don't have a vertex connected. So that's exactly, if you remember in the beginning, it's just approximated for the second derivative, for the second order approximation. But I just talk about the wave equation in this format, take advantage of the graph Laplacian, but yeah, it's not a Schrödinger equation yet. So, but the main point here is that we made use of this incidence matrix. What is this incidence matrix? You can define the incidence matrix like that. You have the columns, the rows that index by the edges, okay, here, and the columns are indexed by the vectors here, okay. So it's pretty simple, the definition of the incidence matrix. So if you have a vertex has a source from some edges, we put 1. Like here, A is a source for the vertex 1, and is a sink from vertex 2, so we put -1. So and after, A doesn't have any connection with other vertices, so we put 0 in the other points. So here is not more a square matrix, but the point is that when you take this matrix here, the transpose of the matrix B, the incidence matrix, times the matrix B, you get the Laplacian. So, yeah, pretty simple. So the algorithm you have to do is prepare the initial state as you want, consider the shape that you want. So then we can apply the different methods for Hamiltonian simulations. There are several methods available. And then here we can deal with this Schrödinger equation. Now here we are working with this block matrix, okay? And then this B here, this incidence matrix. These 2 subspaces that I didn't, I'm talking quickly and superficial about this algorithm, but this subspace is related with the vertex subspace of the Hilbert space and the edge subspace. So if you work with this incidence matrix, you see that only the vertex subspace you evolve like a wave equation, okay? And another interesting thing about this incidence matrix that we can work with different, at least with Neumann and Dirichlet boundary conditions, which is quite important when you do it numerically in different kind of problems. So then in the end, you have to do some projective measurements in your detector region. So that's just an example, illustration of some simulations, a wave packet here that I initialize here. Then I put, for instance, a hole, but this geometry is really poor. It means there's a square following the Neumann boundary condition. And you see that the procedure works, but here I did it only via classical simulations. Just I see the evolution of the amplitudes of the initial state, okay? And then I'm only looking for one subspace. And then see that it's working well. We show that, of course, that we have to certify about the stability of the method, all this stuff. We did it. It is more complete in our updated version. So here the performance of our algorithm compared with the classical one. So as I said in the beginning, classical scales badly with H, because once you have you take the continuum limit, H is become small and small. And if you are working, for instance, with 3-dimensional lattice, where is D here, you see how the running time increase a lot in your problem. And here we are, so we got exponential speed up in terms of the dimension of the lattice D. T is the time of processing, the evolution that you want. And here, of course, that as you are dealing with, again, with a Dirichlet equation, with a Hilbert space, the number of qubits in this space here is D times the logarithm of L over H. L is the diameter of the region that we are trying to simulate. And H is the lattice spacing. So here we can see how we increase this once you have more. If you fix, for instance, the diameter and you want to discretize, take more and more points, you see that the matrix, in the classical case, how the matrix increase. And so to analyze it, we analyze this complexity in time, for instance, using these results here, showed by Barry, Chavez, and Kothari. So as you have all ingredients, we put there in this analysis, so you know there is parts of our matrix, you know how the condition number scales, and so on. So then we could check this using these results. So just a final consideration. So as I said, we showed that we can do it via the Dirichlet and Neumann boundary conditions. It can be established via incidence matrix. You also show how to consider a higher order Laplacians, which means that you are more precise in your numerical. Of course, that you have to lose something, so the complexity increase in this algorithm. And also you show how to proceed with the Klein-Gordon equation, which is a relativistic wave equation, so we can deal with that. This data matrix has properties that we can put associate the mass of the particle. And also we could show how to deal with Maxwell equation. Okay, but now the question is, who cares about wave equation, right? So maybe, oh, it's boring, so I don't care. But yeah, but there are some great companies, big companies that are seek to see some useful application for their problems, right? So there is one, Petrobras. I don't know if you heard about this company. Maybe you heard about, some research that they do, or maybe you heard about some scandals that happen in Brazil, corruption, things like that. But the point here is that I went there, I give a talk, and I show this result, and they become quite interested about this algorithm. Why? Because in their analysis, to figure out about if you have, properties of your oil and gas in deep ocean, they have to do with a lot of numerical of the wave equation. Of course, that the wave equation more realistic, so different kinds of boundary conditions. The velocity of the wave is not more constant; it's dependent of the point. And they work with three-dimensional case. So they complain a lot about the effort they have to do to solve this kind of problem. Because, for instance, in three-dimensional case, they work with around 1 billion points in the simulation. So they have to do it in parallelism, send to several clusters, and they lost several information that they in doing the post-processing after this numerical. So then they invite me to a couple of meetings there, and then because there are some projects ongoing between Petrobras and CBPF. CBPF is the Brazilian Center for Research in Physics, the place that I did my PhD. And coincidentally, they choose Fernando de Mello to probably take care of this fund that you give it to CBPF and to build a team. And coincidentally, Fernando de Mello, who was my advisor during my PhD, and he's here, of course. Then I'm pretty sure that he's a right guy to do this job, and he's a hard worker, and furthermore, he was able to make me a doctor. So I think he can do everything he wants. So yeah, so that's it. Before I finalize my talk, I just okay. I forgot to say that CBPF is located in Rio de Janeiro, and the Petrobras, the Center of Research, the place that I went, is also in Rio de Janeiro. So it's perfect. This combination. And to have an idea, CBPF is, I think around here, something like that. And so the place, if you didn't have opportunity yet to visit Rio de Janeiro, it's a good place to visit afterwards the conference. And before I finalize, I just comment what I'm doing now. Currently, I'm doing my postdoc in the University of Mackenzie, which is located in São Paulo. But now I'm working alongside the totally different things that I did during my PhD. I'm working in the group of laboratory laboratory of natural computing and machine learning. So I work alongside the computer scientist guys, and in this place, I mean, in this place, I work with this Pedro de Oliveira. He's a computer scientist guy, and then I'm trying to apply some methods that they know, like genetic algorithms, things like that, to our problems, to my problems in quantum information area. And at the same time, I work alongside another group there. It's people of graphene. So we're also trying to apply some quantum models of computations to deal with simulations in graphene, like transport properties. So it's quite challenging to me because I have to learn a lot of things that I never see before, like in this side and the other side. And so in graphene, they have an entire building only to focus in graphene, so experimentalists and theoreticians and so on, different labs. So yeah, so make equations every way. Thanks.
Thank you, Pedro, for the very interesting talk. We have now time for quite a few questions.
Thanks, that was a really cool talk. I don't think this was mentioned, but in the implementations, have you taken a look at, so you have a Hamiltonian that you're trying to implement with a quantum computer, yes? Have you given any look at what happens if you can't initialize the initial state quite the way you want to? I know that error scaling and finite difference methods are well studied. How do they compare here? And I don't know, do you have any idea how to address that problem?
Yeah, I mean, in the paper, in the new version, we actually in the first one we have already comments. I mean, the complex about the initial prepare the initial condition, of course, that we have to take in consider. Is a really also tough thing to do, and also in the new version we have an entire section about the smoothness of the function. So then we the smoothness. I mean, like it showed the convergence of this method. You know.
Awesome.
So I mean, it's only 3 pages focusing in this part. Is a lot of calculations. And about the circuit, that's one of the goal alongside Petrobras. I mean, you want to, for instance, use the QCharp software at Microsoft to do the simulations. I mean, so then the first step, you have to build this circuit, and see how it actually scales, and also you have to see the output of interest of they want, and there are several other questions that they will do it for us, and you have to figure out how to do it.
Thanks.
Next question.
Hi, thanks for the talk. I got confused with the input and output of the problem because in HHL, normally you have the output encoded in the amplitudes and you sample from those amplitudes. Can you comment on how this is done here?
So actually, I didn't go deep in the HL algorithm. I just I show it as a comparison with our method, because our method is extremely, it's quite different because we are working with Hamiltonian simulation. About for instance, I don't know if you are asking about that, about the promise for the outputs, or like the post-processing. So if there's the kind of question that you did, we don't have promise because it depends a lot of the initial conditions of your problem. And what more? You asked me about how the HHL algorithm works, right? I mean, no, it's not the same. It's not the same. I mean, it's the same. Only when we consider the initial, the preparation of the initial state, you back to the HH. We make use of the HH algorithm to see our complexity in the initial condition, but only that it's equal.
Any more questions?
Very nice talk. You have used Newman and Dirichlet boundary conditions. Can you use another boundary condition, general boundary condition in quantum graphs?
Yeah, that's a good question. Actually, so far I didn't see methods to work with different boundary conditions, different than Dirichlet and Neumann. But I mean, I assume that you have to see. It's quite important. These different methods, boundary condition, be used for. You have a definition in terms of the incidence matrix, because that's the key point of our algorithm. So, if you don't have, I don't know. You have to figure out about it. Actually, for instance, for the Petrobras, they only care about these two boundary conditions, so it's good for us.
Any further questions? Okay, I just have a bit of a long shot. So, do you think there is some chance that quantum methods can be used to solve nonlinear PDEs?
Yeah. That's a thing that we put in the end of our manuscript. The next steps that we'd like to see. We want to try to do it for nonlinear wave equations, and also we want to because our method is quite. We are applying the difference element method. It's comparable with the classical difference element method. So we want to move it to the finite element method, applying the types of thing of discretization of the domain, and see how we can deal with the quantum algorithm for this other method. So,
okay, thanks. Let's thank Pedro again.